Hello, welcome to Physics Talk, presented by the Quaranteens. I am Dr. H. Today, the Quaranteens have a very special video on temperature. Our video will consist of the following: a description of the origins of temperature, different mathematical examples and formulas about temperature, a differentiation between heat and temperature, an explanation on different phases of matter, and an explanation on different types of thermometers. Last but not least, we will have two very interesting experiments related to temperature, so stick around, you will not regret it. If we are going to discuss temperature, we must go over a brief history lesson of Brownian motion. Let's travel to 1827, where Irish botanist Robert Brown was confused when observing with a microscope a pollen speck that was moving at a constant, jerky, and unusual way. For 85 years, Brown's observations remained unexplained until the theory of relativity mastermind Albert Einstein explained Brownian motion in 1905, and that was the same year that he came up with his theory of relativity. Einstein explained that matter on an atomic level is constantly moving very quickly, and that Brownian motion was proven based off collisions between this pollen speck and water molecules. In addition, it was discovered at this time that atoms and molecules are constantly colliding with each other at extremely fast speeds, trillions of times per second, and they are never at rest. And the random movement of atoms that was discovered was known as kinetic energy, or energy of motion. And the measurement of the energy of motion and the movement of these atoms and molecules is known as temperature. Take note that atoms have more kinetic energy when their temperature is higher. And in addition, the kinetic molecular theory also explains that objects with a higher temperature have more kinetic energy.
Here we have the three temperature scales that measure temperature. This includes Celsius, Fahrenheit, and Kelvin. The main difference between Celsius and Fahrenheit is that they're based on water properties, and while Kelvin is in reference to absolute zero. Absolute zero is the temperature that atoms and matter stop moving. Celsius and Fahrenheit all are based on water properties, and the freezing point of Celsius is 0 degrees Celsius, and the boiling point of Celsius is 100 degrees Celsius. The freezing point of Fahrenheit is 32 degrees Fahrenheit, and the boiling point of Fahrenheit is 212 degrees Fahrenheit. Celsius is a very common temperature scale throughout the world, while Fahrenheit is primarily used in the United States and countries in the Caribbean, such as the Cayman Islands and the Bahamas. With Kelvin, absolute zero is approximately negative 273.15 degrees Celsius, or negative 459.7 degrees Fahrenheit. Water freezes at 273 Kelvin, and the surface of the sun is approximately 5,800 Kelvin. It is not appropriate to say degrees Kelvin, it is just Kelvin. Here we have three equations that show how to convert different temperatures between different scales. And you might notice that the Celsius and Fahrenheit ones are inverses of each other, and that is correct. Here I'm going to walk you through some examples of converting between different temperature scales. On the first one, we are converting Fahrenheit to Celsius, and that is done. The temperature Celsius equals 5/9 times the quantity of temperature Fahrenheit minus 32. If you plug 58, which is the given Fahrenheit temperature for this example, and you plug that in the equation where temperature Fahrenheit is, you'll get approximately 14.4 degrees Celsius. For example 2, we are converting 5 degrees Celsius to Fahrenheit. Now, if you plug in the temperature Celsius in the equation, you will get approximately 41 degrees Fahrenheit. In example 3, we are converting 37 degrees Celsius to Kelvin. This is a much simpler equation because all you need to do is add the temperature Celsius to 273.15, and that will get you to approximately 310.15 Kelvin. Now, earlier in the video we discussed thermal energy. And this is particularly important because now we are going to figure out mathematically how to find the amount of thermal energy per atom. And that is particular with all different types of matter. Now, to find the thermal energy per matter when the absolute temperature is approximately 268.15 Kelvin, we're going to use this equation provided by essential physics. And this equation says that energy is equal to 3/2 times Boltzmann's constant, which is 1.38 times 10 to the negative third joules per Kelvin, times the absolute temperature of Kelvin. Kelvin is also used in different gas laws, such as Boyle's law and Charles's law. So that also is used in this equation. And the solution is to plug the absolute temperature into the equation. And you will multiply 3/2 times 1.38 times 10 to the negative 23 joules per Kelvin times the absolute temperature of 268.15 Kelvin. That will get you approximately 0.24 joules. A longer problem could have you convert from Celsius to Kelvin and then find the absolute temperature, but you're given the energy. So same constant, same equation, just got to manipulate the equation a little bit before.
Next, we will have another scientist discuss the different phases of matter, differentiate between heat and temperature, and discuss different types of thermometers.
Howdy, I'm Dr. W. My job is to explain the 3 different states of matter to y'all. As we all know, the 3 phases of matter are liquid, solid, and gas. These phases are all dependent on temperature. If you want to get scientific about it, it means that the phase of a material depends on the strength of the attractive forces that pull atoms and molecules together compared to the chaotic agitation of thermal motion. Let's break down the differences between the 3. First up, we have solid. Matter becomes a solid when thermal energy is too low to overcome intermolecular forces. The matter freezes and the atoms are stuck together. Solids cannot freeze anymore past absolute zero. At this point, there is no kinetic energy or molecular motion in matter. Absolute zero is at negative 273.15 degrees Celsius or negative 459.7 degrees Fahrenheit. Although solids can still vibrate, they cannot pull away from each other like a liquid or gas can. Solids hold their shape. Water below 0 degrees Celsius is a solid, and it's known as ice. In order for a solid to turn into a liquid, it must reach its melting point. The melting point is the temperature at which a solid can melt into a liquid. For ice, that is 32 degrees Fahrenheit or 0 degrees Celsius. Oh, hey there. Now let's talk about liquid. Liquids have enough thermal energy for their atoms to temporarily break away from each other and switch places. This special quality is what allows a liquid to flow, such as a wave can. However, liquid particles cannot separate completely like gas particles can. For water, it can stay a liquid from 32 degrees Fahrenheit or 0 degrees Celsius up to its boiling point. The boiling point is the temperature at which a liquid evaporates into a gas. Water's boiling point is 212 degrees Fahrenheit or 100 degrees Celsius. Oh, sorry, you caught me doing some yoga exercise. Breathing in and out can be a great way to relieve stress. Why does this matter, you ask? Because the air you breathe every day is a gas. Matter becomes a gas when the thermal motion of atoms completely overcomes attractive forces between molecules. Molecules spread out in a gas and take up as much space as they can. Gas is the phase of matter with the highest kinetic energy and occurs at the highest temperature for an element. Water turns into water vapor if its temperature is at or higher than 212 degrees Fahrenheit or 100 degrees Celsius. Those are the 3 phases of matter. Hopefully all y'all can understand the difference between solids, liquids, and gases. Now let's dive into the difference between heat and temperature. Have you ever thought to yourself, what is the difference between heat and temperature? They sound so alike. They are many times used interchangeably with each other. However, there is one key difference between the two. Let's go over it. To begin, let's define what temperature and heat really are. Temperature is the measurement of the average energy of molecular motion per atom in a substance. As for heat, it is the total energy of molecular motion in a substance. When I say molecular motion, I am referring to the concept of Brownian motion you learned at the beginning of the video. Temperature is an average, while heat is the total amount. For example, a cup of water and a large tub of water may have the same temperature, but the tub of water has more heat as the greater number of water molecules produce more thermal energy. Another name for heat is thermal energy. Thermal energy can be transferred from one object to another, most of the time from a hot object into a cold object. Adding heat or decreasing heat results in a change of temperature. Another important fact to note, heat is reliant upon the amount of mass, whereas temperature is not. To sum it up, temperature is a measurement, while heat is energy. Hopefully now y'all know the difference between heat and temperature. While they are related, they are not the same thing. Next up, we will do a rundown of various types of thermometers used to measure temperature. Now let's discuss thermometers. There are many different types of thermometers, but they all do the same thing, measure temperature. I'll be going over mercury, spring, digital, and forehead thermometers. We'll begin with a mercury thermometer. These thermometers are the most common type of thermometer. Mercury thermometers consist of a glass tube filled with the element mercury. When the glass tube is dipped into a substance, the mercury will rise or fall depending on the temperature. When mercury is hot, it expands, and it shrinks when it is cold. Read the degree marking on the margins where the mercury stops to tell the temperature. Mercury thermometers are most used to measure tangible substances such as liquid or food. Next up is the spring thermometer. These thermometers involve a heat-sensitive coiled piece of metal that expands as temperature rises and contracts as temperature cools. This action causes the pointer to move and land on the temperature measurement. Spring thermometers are built to measure pressure. Now we'll discuss digital thermometers. Digital thermometers contain heat-sensitive liquid crystals to display the temperature. Commonly used for kids, these thermometers measure a body's temperature by placing the reading stick under the tongue, under the armpit, or up the rectum. Digital thermometers are regarded as the fastest and most accurate thermometers. They can be easily found at your local pharmacy. Finally, we have forehead thermometers. Forehead thermometers are handheld machines held at the forehead that measure temperature using infrared. These devices read people's temperatures by scanning the temporal artery on the forehead that is connected to the heart and can tell if someone has a fever. Doctors commonly use forehead thermometers on visiting patients. A spike in forehead thermometer usage has drastically risen due to the COVID-19 pandemic to avoid infection between doctor and patient. I'm an expert on thermometers. I'm not sure how far that information will take you in life, but now you know. Sadly, my opportunity for teaching y'all has reached its conclusion. This has been Dr. W. Over and out.
With all this talk about mathematical equations, temperature can get a little confusing. Let me provide a real-world example for you. Let's say that the outside temperature is 75 degrees, and then you have a 75-degree body of water, such as a pool. If you get in that body of water, most likely it'll feel colder than the outside temperature. Wow, this pool feels quite a bit colder than the outside temperature, even though they're the same temperature at 75 degrees Fahrenheit. Why is that? Well, it all has to do with the conductivity of these mediums, which basically means how fast is that water or air pulling heat out of my body. And as it turns out, water is actually a better conductor of heat than air is. So it'll pull more heat out of my body more quickly than air will, which is why I feel colder in water than I do in air. What if I told you that you can hear the difference between hot and cold water? In this experiment, I'm going to be covering up the camera lens and then pouring 1 cup of hot water and 1 cup of cold water in no particular order. Your job is to determine whether I pour the hot water first or second. So which cup had the hot water in it? Cup 1 or 2? If you guessed cup number 2, then you would be right. Because cold water has a higher viscosity than warm water, that means that it bubbles less when it is poured. Therefore, a lower frequency sound is emitted.